Problem number 4. Take-home exam 3. This was a big problem. And because the chemicals involved are kind of big and hairy, and largely a whole bunch of it is not even important, I'm going to abbreviate what we need to focus on. So this had a carboxylate over here, and then there was an aromatic ring over here. I'm going to ignore that because the important part is basically just this bit down here. So this is our BN, I think it was a beta-lamic acid. And what we have here is in the first part of their transformations under aqueous basic conditions with a pH of around 11, they convert this iminium ion, so it's basically an imine with too darn many bonds around it, that's why it has a positive charge, and they convert that to the aldehyde. In other words, they are cleaving that right there to, if you will, give back the aldehyde from whence it came. So how does this work? Well, it doesn't take a rocket scientist to see that this should be a very good electrophile because I got a positively charged nitrogen there. It's kind of like a carbonyl already. It's just a nitrogen instead of an oxygen, and like I said, better yet, it's got a positive charge. So if I have a good nucleophile around, which of course I do in the form of hydroxide, this is really ready to go and react at that carbon to give me this guy. And again, I'm just going to abbreviate these things wildly. So this has a hydrogen on it. The rest of this is untouched. Nothing to see here, nothing going on here. All right, so I've added my hydroxide. Clearly, at some point, eventually, I'm trying to get rid of that, right? But I'm under basic conditions. So this is a question. Is this a good enough leaving group that my base could kick it out? Because if it is, then I'm done, because that electron movement I've just shown there is certainly going to lead to the product. And that's, that's legitimate. N minus is a very, very strong base, though. So that's a possibility. It maybe is not the best possibility. So what about protonating this first? Could this be protonated under basic conditions? Well, what would I protonate it with? Well, my only conjugate acid is water. And so the question now becomes, is this reasonable under basic conditions? And I think the answer to this is yes, it actually is. Because this is not a particularly strong acid. In fact, it's not a strong acid at all when you look at what we're using as our reagent, ammonium hydroxide. It's pretty evident that a positively charged nitrogen can exist under these conditions. So, best to go ahead and protonate that first, and then we can go ahead and, better yet, draw this out so that we can clearly see the electron movement removal of that hydrogen slaps down, kicks that out, and we've generated our aldehyde product. So it's a very straightforward mechanism. You just need to pay attention to whether you're under acidic conditions or basic conditions. It has nothing to do with any of the rest of the molecule. Now the next mechanism continues along the chapter 17, 18, 20 spectrum by going from that aldehyde and let's see, this is this guy again. Now we're going from here to let's see, no, I got that one in the wrong place. Here and here and here. This somehow or other, under acidic conditions, goes to this guy. So now the rest of the molecule is involved somehow or other. And again, I'm abbreviating. I will admit I'm abbreviating because I don't want these mini lectures to be astronomically long. All right, so here's that guy, here's that guy. So, acidic conditions. TFA is trifluoroacetic acid. That's a very strong acid. So the very first step that's going to happen is protonation of my carbonyl to make a much stronger electrophile. So I've now gone to this guy so that whatever nucleophile is going to react is going to do so a lot more readily because, like I said, I got a nice strong electrophile now. So it's quite evident that this is my nucleophile. And what else is evident is if you look at the product is that somehow or other this is the nucleophilic carbon. So what I should be looking at is some resonance contributors that show how there's a big fat glob of electron density on that carbon. And it would be a good idea to make sure that we all realize that there's a hydrogen on there. And that would be positively charged. This is my resonance my resonance contributor. It's not a great one because I've got two formal charges, but it certainly does show why this carbon would react with that aldehyde to give me what is, fairly close to my product. Okay, so I got a methyl group there and a methyl group there. This goes down like so, dot, dot, dot. Okay. All right, now what? Well, let's clean this up just a hair. That looks like a double bond. I don't want it to. Okay, so I'm not home free. Clearly I need to get that nitrogen, get its lone pair back. And if you look at the product, there's a double bond there. So I think I had better figure out how to do an elimination for that hydroxyl group. And there's a bunch of different ways you can do this. If we pay darn close attention to our non-line structure, we know there's a hydrogen there. And I could do that. Psst, I don't like it. Why don't I like it? Because I'm under acidic conditions. And it makes a lot more sense for me to protonate this first. And if I protonate that first, I'm going to squeeze this in down here. Am I going to squeeze it in down here? Nope. I am going to turn things around here and make room to go back the other way. Okay, so now I have this guy and my protonated amine type thing. I have this guy, great leaving group now, and the rest of the molecule. All right, well, makes pretty good sense for this to leave. Gives me carbocation. And all this is actually just good old review of like E1 versus E2. So I end up with that carbocation and the rest of my molecule. And so now I can use a nice weak base like the conjugate base of my trifluoroacetic acid to come over here, pluck that off, and that gives me making more room again. I just don't have a big enough blackboard here. I'll send us way over here. That gives me this guy. And we're a stone's throw away from our final product, because now all I have to do is plop these here, 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 here. Woohoo! And then I have beet blue. So, a little proton transfer activity, a little leaving group loss, a little electron delocalization, and you're set. So that is basically problem 4. I will show you exactly what I was looking for in problem 4C. So here is our one resonance contributor. And what I needed you to show me is how this basically interchanges, not interchanges, is in, can delocalize its electrons to give the resultant resonance hybrid, which the paper shows in the middle is just a hell of a delocalized mess all the way up through, let me do it with the highlighter. All this is delocalized. So what does that look like? Well, it's kind of the opposite of what we showed in the previous slide. Basically, all you need to do is push the electrons from the amine back down, 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 and give it back to that positively charged nitrogen. Hoofda! So that results in this guy. Which we saw on the previous slide, if you will. All right, so that is problem number 4 in its entirety.